Good evening. It was good to see many of my old friends last night. I'm just sorry I couldn't join you with my presentations, but sometimes the grim ones do appear. I first want to thank Susan Nash for inviting me to this AAPG webinar entitled Pivoting 2021 Energy Industry Supply Chains. I just want you to know that I'll be giving you a brief insight into what's going on in the uranium supply chain and in the rare earth chain as well. I've been involved in uranium in the 60s and 70s and on and off on other projects as uranium and nuclear power issues came up, as well as rare earths, both of which occur together. And that's why, in many cases anyway, and that's why we included in the EMD Uranium, Nuclear, and Rare Earth Committee. I want to share with you also some of the issues that are, let's say, plaguing the nuclear industry. Starting with, of course, the fuel issue. This is from the U.S. Congressional Research Service last year or a year before last. It gives you a good idea of what the overall supply chain looks like for nuclear fuel. You notice on the left over here, this is where the mining is. That can, of course, can be either in situ mining or open pit or underground mining. We have a number of projects in North America, and I include in that Canada, of course. I could talk more about the Canadian mines, but they will no doubt come into play in our use of uranium. But in the U.S., as I discussed earlier, well, late last year in a presentation, the name of which was Uranium and Nuclear Power is on the Move. You might want to check that out for more details about what's going on in terms of what our ability of mining in this country from roll fronts and other deposits that may or may not ever be developed. But the fact is, the supply chain starts there. And do we have reserves? In our judgment, yes. Now, when I say our, I'm talking about the committee and my vice chairs and advisory groups that we get together from time to time to discuss these on the telephone, of course. But I'm sort of their mouthpiece and have been so since when, maybe 2004 when I was first appointed, and how the time does fly. But the fact is, getting back to the supply chain, since I have only a limited amount of time here, we first of all have to worry about these inventories and make sure they're going to be available for the fuel to make yellow cake, and then the yellow cake has to be turned into uranium fluoride. It's a gas by enrichment. Because we're trying to upgrade the uranium fuel from containing mostly U-238 with only a little bit of U-235 up to where the U-235 is useful in U.S. reactors. Now, how is that done? We'll discuss that in a minute, but just for a general discussion, you have to realize that it's enrichment and then fuel fabrication before it can be loaded into a reactor. The problem with the supply chain is that many years ago, whether it was because of pressure to move overseas for maximizing profits from the utilities, or was it environmental issues that prohibited such things as converting this yellow cake into uranium fluoride and other enhancements, or whether it was both a combination. I remember Jimmy Carter's, while Jimmy Carter was president, he refused to support this enrichment aspects. And so I suspect that and a lot of the environmental concerns about uranium in the 60s and 70s probably drove a lot of this overseas. Now, as I discussed in this 2020 presentation, we've been getting a lot of the uranium to start with anyway from overseas companies, and I mean countries and foreign countries, and I mean overseas, such as in Russia and Kazakhstan and Uzbekistan and other places like that, that makes it a little unsecure in terms of anything happens to our supply. And that's why earlier this year, the government, the U.S. government, has decided to come up with a plan to help protect some of our supplies and encourage the American uranium mining companies to start putting fuel into the supply chain as soon as the price rises, so that it would be reasonable to have these companies start up again. Now, the reason the overseas countries can produce uranium is because many of those are produced with government support or allowances that keep the price down. Now, whether the American utilities were going for the lowest possible price, that's another issue. You don't blame them. This is a capitalist society. They're trying to optimize the profits. But the fact is, the uranium fuel costs in a nuclear power overall economics is only something like 5% of the operating costs. So it always boggles the mind as to how far can they take the cost down in their fuel. But the fact is that will change here in a little bit, and as we move forward, even some of the enrichment will come back to this country, and fuel. I think this fuel fabrication into the final product has always been, well, generally done in the U.S., and there's less and less because the fuel that actually goes into these reactors are not highly radioactive until they put in a fissionable environment, which let's call it heats them up. Okay, let's go on to the next slide here where things get more interesting. This overall flow, this is a more detailed map, let's call it, of what we were looking at earlier, and starting with mining, in situ recovery, going into this conversion, it takes yellow cake to the uranium fluoride, and into the enrichment, into the fuel, into the reactor, and then into interim storage here, and into the spent fuel. Now, the spent fuel issue has always been a problem, at least with some people, that this being extremely radioactive, which it is not. Once it's used, it's finished in a reactor, there's still a lot of energy, and only 5% of the energy has been lost in those pellets. Here's a pellet down here, and these are stacked in these things as they go into the reactor. But the fact is, we should be thinking of this waste product as not as an issue that is to be feared, but we got to put it on the shelf, store it, and that's what the Yucca Mountain storage facility was supposed to do until things got a little complicated with potential groundwater issues, and that's why it's been difficult to get that finally into operation. Whether it does or not, I can't tell right now, but we'll see. Right here is to give you an idea of what in situ mining looks like, closely spaced drilling, and here's some of the wells that are drilled. You see, you put in a oxygenated fluid, it runs in here, is taken out, and then sent to a processing plant, and then that's where this ends up over here into the conversion and in other departments in other parts of the country. And these are typical flow patterns in and around a in situ mine. Now, these are gaseous centrifuges that handle a lot of this transitioning from 0.07% U-235 as it comes out of the conversion from the uranium fluoride. It should be on its way by using these centrifuges to a maximum of about 3% of U-235. Now, that's what these pellets consist of. This is an issue because once this heads higher, the centrifuges to make nuclear weapons, for example, this number has to be up somewhere around 90%. So you can imagine if this takes weeks to get this gaseous diffusion going on to separate out the 238 from the U-235. Imagine how long it would take to take this 3% to 90-some% for nuclear weapons. Well, Iran and other countries that are still making nuclear devices, i.e. bombs, they have to do that, and it takes a while. But that's where the difference splits off from nuclear power generation to nuclear weapons. And it should be clear along those lines. So let me remind you that there's more very good information here available for Jim Conca. Right here in the bottom of this reference, this is he's a member of our advisory group, the Uranium Committee's advisory group, and this is a video addressing these storage issues on waste, and I recommend that you have a look at that. Okay. The fuel costs are incredibly important in one sense, in terms of when you're looking at whether to build a nuclear power plant or a gas plant. Because when you look at the economics, we put together these numbers a few years ago, and we ran across Dr. Ruzic down here has incorporated a lot of the similar kind of assumptions of how the difference between putting a nuclear power plant together versus a natural gas plant. And of course, what sticks out a lot is the capital costs are very high, relatively high for nuclear power plants, and fairly low in natural gas plants. But here's a very interesting thing: the cost for fuel per year in a nuclear power plant is usually right around $64 million. Where in a natural gas plant, the fuel costs are about $450 million. Now, back to the negative side on nuclear power plant construction is it takes around 6 or 7 years, if not longer. But let's call that 7 years, and let's call it only 3 years for natural gas. And an interest rate, let's call it equal. And in order to repay for, let's say, loan purposes on the $6 billion, the nuclear power plants would have to come up with about $285 million payment per year, whereas natural gas only have to come up with $57 million. Now, this is an issue here that has to be factored in, and that's electricity sales. This is based on a 1,000 megawatt plant. And you can expect somewhere around $525 million a year. Now, that being said, if you work out the economics, you'll notice that for the first 10 years or so, natural gas plants are built faster, have lower capital costs, but natural gas costs are about 7 times higher, as we saw up in the table. Now, natural gas plants pay off in about 10 years in the economics of it. And large-scale nuclear power plants pay off in about 25 years. Natural gas plants' lifetime is about 15 years, whereas nuclear power plant lifetime can be greater than 50 years, and similar to most hydroelectric power plant projects. Nuclear power plants generate much greater profit, however, over a longer period of time than natural gas plants. And not only generate greater profit, but when you run it out into the 40-year basis, like you would in a hydroelectric plant economic assessment, you would see that the nuclear power plants generate an incredible amount of profit over the years in the long term, not the short term. Natural gas plants are built and operated on the basis of the short term. Nuclear power plants should be considered in terms of being built in the long term. With the introduction of the SMRs, the small modular reactors, the new technology, Economics is going to be all changed up. You're looking at for three units that would give you about 1,000 megawatts of electricity. You're looking at about 1.5 million, 1.5 billion, as opposed to 6 billion in this standard plant. You're still talking about 64 million for fuel. You're still talking about construction time. You're only talking about 3 years construction time for these small units, as opposed to 7 years for nuclear power plants. And repayments would be a lot less, but you still have the same profit. As you can get a sense right off, these new small modular reactors, the SMRs, could have a dramatic impact on the whole economics of generating electricity in this country and around the world. And so I would suggest that for the proof in the pudding, as it were, I would have a look at this economic model discussion by Ruzick. He does an extremely good job. I was very impressed with his treatment of these factors, and I recommend you have a look. Okay, let's go to the assessment of the U.S. rare earth element supply chain. You should note that the annual global rare earth market is about $8 billion in 2018. But the U.S. only consumes around 7% of the global demand of our rare earth elements by weight. And then the U.S. imported about $160 million worth of rare earth compounds and metals, while importing $2.6 trillion worth of finished products. Now, that's $2.6 trillion. The majority of the rare earth elements imported in the U.S. is in finished products and not as raw material. In other words, we're not getting deposits, our rare earth oxides sent in because China has such a hold on the market right now. But the U.S. government is now supporting domestic production, like they are with uranium. They're giving uranium a special treatment, and now also in rare earths, which we're glad to see. China, however, it should be noted, and surprised us all last year, sometime when we first learned about this, China has become a net importer of rare earth elements associated with permanent magnets. Because there's such a huge demand of magnets, they don't have enough of the neodymium and other rare earth elements that are used in dysprosium and all that, that are used in batteries. And yet battery final product, permanent battery is driving the export out of China. And China will probably be importing more rare earths by 2030. Summers, this reference down here that we ran across from one of the national labs has come up with. With that in mind, also last year, my group put together a rather extensive coverage of rare earth elements. I think the title was something like Sources of Rare Earths in the U.S. and the world for rare earth elements. And I mentioned, and I want to emphasize here, that this business that China started to become a net importer is coming to fruition, in that China has gotten an agreement and a piece of this Greenland Minerals that is active in Greenland and the southern tip of Greenland, and is making deals with Australian companies to get pieces of those companies as well. They're setting up for that import, and now we see it happening. Of course, there's going to be a growing world demand of high tech and green technologies. We all know that, and changing markets, however, could stabilize and even increase rare earth market prices for high demand compounds for specialized applications. What I want to emphasize here is additional uses of more abundant rare earths is still needed, and exploration and opportunities for exploration may develop soon. We're working on, and I know there's other groups are working on products or projects in Alaska that I mentioned in one of the previous presentations, that on the Seward Peninsula, the eastern part of the Seward Peninsula, where uranium, thorium, and rare earths and substantial concentrations occur. And same with the Bocan Mountains down in the Alaska Panhandle and elsewhere in the world, in those kind of igneous metamorphic rocks starting to become of interest. Over the years too, I mentioned in the discussion I had a couple months ago in the presentation on rare earths, I mentioned that there's the rare earth recovery from coal-based feedstock and coal ash waste has been proven to be reasonably technically feasible, I should say. And so I think there's going to be a lot of action there. I've got to mention at the same time that the California rare earth project that had been producing rare earths for years and then ran into some economic issues. A good piece of that was also bought by Chinese and other foreign interests, but they apparently are still doing some production. But there's also a mine in West Texas here that's about to start up, and we're hoping to put together a field workshop, a field trip to the mine in West Texas that's, as I said, about ready to start up sometime this fall or early next spring. So I would keep your eyes out for that. We'll get that message out. So let's see, the research is from what we can see is continuing to proceed, and as is usual, research always looking for replacements for rare earths in many finished products. That's a typical research objective. Is if it's costing too much to do it from one material, then find other materials that would do just as well, if not better. So it's definitely, we're hoping that the U.S. rare earth industry will be developing and will be coupled with a domestic supply chain soon. But even with the successful domestic rare earth industry, China will continue to control, we understand, the rare earth market for many years because they are producing and marketing finished products containing rare earths to the world. Again, I would recommend you have a look at this Summers from one of the national labs, and this this is the paper or the presentation we put together a few months ago. Over here is a highlight from one of the reporting services that I'll hit on briefly. This tells you about how the U.S. government's starting to fire up in terms of supporting some of the activities in the U.S. This is an indication that the Pentagon is playing a leading role in by citing the Defense Production Act to encourage domestic rare earth mining and energy fuels. One of the classic, one of the well-known American uranium companies, Energy Fuels, has gotten into the rare earth business by having come up with a rare earth concentrate method from monazite sand in Georgia or somewhere down in the southeast that they've got now in operation or about in operation in the White Mesa mill in Utah. Also, I can tell you that there is a deal developing in for the Texas to handle the Texas product and maybe the California mine for processing the rare earths produced at the Texas mine in setting up operations in Denver, and I believe that's part of this overall energy fuels, and the mine in Texas. They're getting together, discussing issues. And the interesting thing is the Chemours company. If you haven't heard that name before, that's because it's a fairly new company. It's actually it used to be a part of DuPont, and DuPont I worked for I was regional technical manager here in Houston for the environmental group that looked after all the issues. And DuPont decided to split up into some projects will go with Chemours, wholly owned, separate, and then others will stay with the parent DuPont. So, but Chemours is getting quite active in this project with the monazite ore, and in fact, I think that is their property in southeastern United States. Also, this reports that Apple is finding ways to get out of China, and some of the renewable energy folks are looking for ways to put their generators together with rare earths in a more, let's say, direct manner rather than having to depend on China. So with that in mind, I have indicated down here there's a reference for the looking at this in greater detail. All right, this from one of my previous presentations, a map of the historical trade routes of the major rare earth sources and rare earth refineries. And as of 2014, and this is the actual paper that this came out, this particular graph came from. I recommend you have a look at that. It's very interesting reading, actually. And this gives you sort of the flow of China dominating. This is where the products leave. And this is Mountain Pass, the California rare earth mine that I mentioned earlier. It used to send all of its product back to China here. This is coming here, back into China. And these are some of Chinese deposits, which are substantial. They must be, with their recent emphasis on looking for partners and making acquisitions of companies, these mines may well be seeing the end of their lifetimes, although there are 3 or 4 deposits they haven't developed, but some of them are like the projects we're working on over here in the Seward Peninsula. They've got a lot of uranium and a lot of processing issues to them, and that may be starting to slow up some of their activity, but they're still dominating the manufacture aspects, and that's why they're looking for imports now, not only from Greenland, from here for this particular Greenland Minerals right here, but also from Mount Weld, and there are a few other, quite a number of actually rare earth deposits in Australia. So this requires some special study as well. I recommend this paper, of course, and also I've referenced the rare earth paper we did. And the bottom line here is the historical trade. These trade routes that are showing here, they're all changing. Russia's getting into it more and more. They have a few mines that are of sufficient value to start producing and bringing a lot of their material from the Kola Peninsula here into play. But most of their product, as you can see here, has been always to Japan. Japan and China have been at it in terms of competition over the years, but China has been eclipsing, and Japan is still in there swinging. I must say, a lot of research is coming out of Japan. So with the supply chains in flux and the specific rare earth demand increasing, especially in magnets, it ought to be interesting how things come along. And I and I think we in my committee we all agree that the U.S. is starting to look after it, and I think Biden understands what's going on. He is definitely pro-nuclear, and he's pro rare earth development. So I think with that in mind, I'll begin to close here by saying that if in fact you want more information, you'll see in back of this on the PDF that there's a link to what we call the I2M web portal that has close to or more than 10,500 records now, most of which are either uranium, thorium, rare earth, climate related, and other things that we deal with in our company within I2M consulting, but also in what we deal with in our annual reports, which we're working on now. We're working on the 2020 annual report for the Uranium and Nuclear Rare Earth Committee that should be finished in this is what April, May. Hopefully in the next month we should have that ready. And this is a link. I suggest you get a copy of the PDF version of this presentation, so you'll have direct access to the links that we've included. So on that basis, let me say again, thank you very much, Susan Nash, for inviting me. I appreciate it. And if you have you and anybody that might see this video as part of your webinar presentation, I'd be glad to talk to people. So feel free, and I look forward to the next webinar that AAPG comes up with. Thank you.